Welcome to RSSL's second in our autumn webinar series, Introduction to Disinfection in GXP Environments. For those of you that attended any of our webinar series, welcome back. If you are tuning in for the first time, my name is Annette Russell. I'm the Sterile Manufacturing Lead here at RSSL. My role is to help facilitate clients with requests supported by a team of experts in the field. This is the second series of webinars that we've put together for our Sterile Manufacturing webinar series, and I would encourage you to take a look at the previous 5 webinars we have run, as there are some really interesting and hot topics covered in them. These can be found at our website, www.rssl.com. If after the webinar you'd like to learn more about our offerings, please contact me direct via the email or telephone number on your screen. With the announcement last week of the new Pfizer and BioNTech vaccine and the Moderna vaccine having over 95% efficacy, it starts to feel like we're heading towards the end of this strange period in history we've been in. And it got me thinking about the status quo bias that you can see in front of you. Most people don't like change, and it's something that they try to avoid. But in this period, we've had this thrust upon us, and it's something we've learnt to live with. Here at RSSL, I'm lucky to work with a team that will embrace change. A couple of years ago, due to the expansion of the pharmaceutical microbiology team, they moved into our new purpose-built site at Wokingham. And not long after, they set about designing and building and qualifying our new sterility suite. Finally, more recently, once the sterility suite was up and running and COVID kicked in big time, our technical teams all adapted to the way they work to ensure that we could assist our clients in their fight against both the virus and the effects the virus causes. So RSSL's analytical support for sterile and non-sterile customers. We have a range of dedicated and flexible team members that can help offer a variety of different analyses to help you. We are able to offer services such as endotoxin using the Lal method, sterility with our new sterility service launched this year. The mycoplasma testing is coming soon with fast mycoplasma to follow. We can do raw material testing. We can help with your vial and stopper analysis. And we can do routine and we can do investigative problem-solving analysis on any particles that you might find in your fill-finish line that you want to investigate. We also have the capability of helping with disinfectant and cleaning validation, and we can support environmental monitoring of both existing and new facilities, as well as supporting any training or consultancy requirements that you may have. In fact, we keep changing here at RSSL as we improve our services and better support our clients. So coming soon, at the end of November, we're looking to offer our MALDI-TOF fast and accurate identification to supplement some of our other services. I'd now like to introduce you to our guest speaker, Dr. Tim Sandle. I'm sure many of you have heard of Tim and to subscribe to his many publications. Tim has over 25 years experience of microbiological research and biopharmaceutical processing. Tim is a member of several editorial boards, and he has written over 600 book chapters, peer-reviewed papers, and technical articles relating to microbiology. Dr. Sandle works for a pharmaceutical manufacturer in the UK and is a visiting tutor at the University of Manchester and UCL. Over to Tim.
Okay, so hopefully you can all see the slides and hear me okay, and it's a pleasure to be back with you again. So we're going to try and cover what was quite a big area. So we're going to sort of touch on some of the key aspects relating to cleaning and disinfection and tie this up to what the global GMPs are actually asking for. So we're going to have a look at the global guidelines for disinfection and cleaning of clean rooms, touch on what the revised Annex 1 is saying, and also what some other applicable standards are saying, such as USP chapter 1072. And then we're going to look at how we need to use disinfectants effectively. What are the key points for success and some of the practical tips, and looking at some of the science that underpins that. And then some of the differences between the approaches in Europe and the US. And then we'll also have a look at validation and also touch upon some of the regulatory requirements as well. So just to kind of set a baseline to clarify some objectives in terms of what we mean by cleaning and disinfection. Well, cleaning is important, and it does differ from disinfection. So we define cleaning as the process of removing residues and soil, that could be dirt, dust, protein, skin cells and so on, from surfaces to the extent that they are visually clean. And this is important because a disinfectant will not work properly if there is a presence of soil, particularly grease and protein. And that's because the disinfectant needs to be able to reach the microbial cell wall, and the soil acts as a barrier. And it's for this reason that the revision to EU GMP Annex 1 puts a particular emphasis upon cleaning, and we discuss that later. Now, with disinfectants, these are chemicals designed to kill or to inactivate microorganisms. And there's a number of different types of disinfectant with different modes of activity and varying effectiveness. And the objective is to achieve a targeted reduction in a microbial population. And it can also extend to where we have concerns about particular organisms of concern. And this is also where the concept of rotation comes in, which we'll also touch upon. That relates to extending the mode of activity and the spectrum of kill that we can achieve. Another important factor is the class of the clean room and what kind of level of microbial control we want to achieve. But as it stands, cleaning and disinfection are both essential to a biocontamination control strategy, and that also connects with Annex 1. So if we said that cleaning is the targeted activity of removing residues from a surface, and this is to the extent within the clean room context of ensuring that surfaces are visually clean. In the context of cleaning validation, then there would be assessments with swabs to detect total organic carbon levels and so on. But in order to achieve appropriate cleaning, we need defined methods of application together with the use of an effective detergent. And although there are some cleaning products that do contain low levels of antimicrobial substances, we shouldn't think of cleaning as being an antimicrobial step. However, the activity of cleaning can help to remove or dilute microbial populations and also help to disassociate organisms from surfaces, which is again another point which we'll come on to. So in terms of using a detergent, detergents work by penetrating soil, and they reduce the surface tension, which is the physicochemical forces that keep dirt or a microorganism attached to a surface, which is why many detergents are also known as surface active agents or surfactants. And detergents will often contain differently charged ions that will also cause microorganisms to repel one another. And it's also this act of repulsion which also helps disassociate microorganisms from the surface. And then it's these suspended microorganisms that can then be more easily killed by a disinfectant. So this is what's referred to as having microorganisms in the planktonic state. So you kind of think of free-floating plankton in water. They're far easier to kill than microorganisms adhered to a surface, which is known as the sessile state. So disinfection is either killing or inactivation of microorganisms. And disinfectants can be classed as either those which are microstatic or those which are microcidal. So with the microstatic effect, it's rendering the organisms unable to reproduce, but that static effect only lasts as long as the disinfectant is in contact with the microbial population, whereas the microcidal effect is about killing the microorganisms outright. In terms of terminology, we tend to use disinfectant for an inanimate objects. That might be all the surfaces, equipment, and so on within the clean room, whereas antiseptic is reserved for skin. And apart from the chemical disinfectants, which is the focus of this webinar, then there are other forms of disinfectants, like the application of heat or ultraviolet light. Another important thing is when we're defining disinfectants is that to be classed as a disinfectant, the chemical does not necessarily need to be able to kill bacterial spores. And in fact, most disinfectants on the market are not sporicidal. So we do need to purchase specialized disinfectants for that purpose. And again, I'll say something about that shortly. So we've defined disinfectant as this diverse group of chemicals, and we touched upon some of them having a static effect, which halts growth, and some which have a cidal effect, which then destroys cells through different irreversible mechanisms. Now, there's numerous ways to classify disinfectants. One scheme is to group disinfectants as non-oxidizing disinfectants and into oxidizing disinfectants. Now, with the non-oxidizing disinfectants, these tend to have very specific targeted modes of action against microorganisms. And by virtue of having this targeted action, it often affords them a slightly more limited spectrum of activity. So within this group, we have alcohols, aldehydes, amphoterics, biguanides, phenolics, and quaternary ammonium compounds. So particularly with the alcohols and the QACs, these are amongst some of the most common standard disinfectants used in pharmaceutical and healthcare facilities. And then we have the oxidizing disinfectants, which tend to have non-specific but more wide-ranging modes of action. So they have a wider spectrum of activity. And the majority of these are sporicidal. So here we have the peracetic acids, hydrogen peroxides, and the chlorine-based disinfectant compounds. Now, I've spoken about different ways that disinfectants kill microorganisms. So here's a very simplified diagram of that process. So if you can imagine, the picture is a bacterial cell. And here we have different disinfectants which are in the red font, and the different parts of the organism which are in black font. So different disinfectants will kill bacteria and fungi as well in different ways. They will cause things like the leakage of cell material. They will cause protein denaturation. They will cause the coagulation of cytoplasm, or they will block ion transfers, or they will cause cell lysis, effectively causing the cell to rip open. And this is what's referred to as different modes of activity. Now, the reason that's important is that when you embark on a disinfection rotation selection exercise, as Annex 1 requires, then it is sensible and might risk regulatory criticism if it wasn't, that the two disinfectants you select have different modes of activity and slightly different spectrums of kill. So you're ensuring that you stand a greater chance of eliminating a microbial population. I mentioned earlier sporicides. So this is a separate class of disinfectants. So to kill spores, endospores of bacteria and fungal spores, you need a disinfectant with sporicidal properties. Occasionally you'll come across this term high-level disinfectants, but I think sporicides are a clearer definition. And of course, as well as killing spores, these agents will also kill all the vegetative cells. And we have a good definition in the USP chapter 1072 that informs us that the sporicide works well when it's used in appropriate concentration for a sufficiently long period of time. The downside with a lot of sporicides is that they're quite nasty to use and do present greater risks to human health. So PPE is important, and some even require personnel to wear respirators and so on. In terms of regulations, the main regulatory documents that we need to be mindful of that refer to the use of disinfectants in pharmaceutical manufacturing are the US Code of Federal Regulations, and I've selected there the most pertinent parts of the CFRs, which refer to sanitation, equipment and maintenance, a cleaning program, which also by inference is a disinfection program, and the control of microbial contamination. There's also the FDA Aseptic Processing Guide, the USP Chapter 1072, which is a guidance chapter. There is a Pharmaceutical Inspection and Cooperation Scheme PICS document on the validation of aseptic processes. And then we have Annex 1 in both its current form and in the revised form, which happened to be the subject of the first of this RSL series, and I think is still available for viewing. Now, if you start to look at these regulations, then there's key topics, and also if you look at the key findings from various inspections by regulatory bodies, and it takes a while to unearth this information, but I have done an exercise of looking at this. And when I was searching for my notes for cleaning and disinfection, then it's interesting that contamination control for the last time the MHRA published their figures accounted for nearly 10% of all observations made by MHRA. And that was also in relation to things like environmental monitoring not being tied up appropriately with the cleaning and disinfection regime, inappropriate use, so you didn't have effective environmental control, or where there were weaknesses that could lead to microbial contamination. Taking a look at the FDA warning letters published, then we find that 16% of all audit observations relate to cleaning and disinfection. And there were, I think, 65 observations relating to cleaning disinfection, and it stood as the 8th most common finding from FDA inspectors. And then various deficiencies were things like records not being kept, the procedures themselves being seen to be ineffective, procedures that may be in place not being followed, and just the overall deficiencies in actually achieving the objectives of contamination control, and in some cases that tied up also with pest control as well. Okay, so that's some key things from regulations and regulatory findings. Now, let's look at this issue of rotation, which is embedded in EU GMP Annex 1, but is less clear-cut in the various North American regulations. But typically, 2 disinfectants need to be rotated. Now, there is the expression in Annex 1 that sometimes causes confusion, which is about resistant strains. And by this, it isn't so much a reference to organisms acquiring resistance to a disinfectant as they might to an antibiotic, but it's more that the overall pattern of cleaning and disinfection is inadequate to destroy those organisms that are harder to kill. So this is where you need the 2 different modes of action in order to get that sufficient level of activity. And it's perhaps why Annex 1 is now requiring the use of a sporicidal disinfection as part of that pattern. And in some senses, the EU GMP reference also ties up with the FDA guidance on aseptic processing, which does talk about the use of a sporicide, but not necessarily part of a formal rotation program, and in USP 1072, which also talks about the periodic application of a sporicide. It's only in the revised Annex 1 that the sporicide needs to be incorporated into the rotational regime. So speaking of the revised Annex 1, this is obviously the subject that we went into at the beginning of this series, but it's notable within that the references to disinfection have been substantially expanded. So rather than covering less than half a page, it now extends to about 3 pages. The need to rotate very much remains, but there's now the requirement that one of these should be a sporicidal agent. Cleaning is given much greater prominence, particularly about the risks of residues remaining and the importance of removing those residues. There's a big emphasis upon disinfection qualification. And this is not just the initial qualification, but an extension to considering things like all the different surfaces that are within the facility. And there's also requirement to assess the bioburden of non-sterile disinfectants and also to assign expiry times. So there's a taster of what's in the annex, but if you want to listen to the previous recording, there'll be some other aspects that are in there as well. Now, disinfectants may work well in theory, but there's a whole array of factors that can affect how well a disinfectant works in practice. And this very much depends upon the level of biocidal activity that disinfectant possesses. And there's also variations with the concentration. The concentration does not need to be out that much for the disinfectant not to work. So if you're diluting down concentrates of disinfectant, that's something to bear in mind. Contact time is important, and I'll explain about that in a minute or two. The nature of the surface to be disinfected, that includes the age and type of material. The type of water that's used and the relative hardness of that water. The harder the water, then the more risk there is of ions that will counteract the active ingredient within the disinfectant. The level of organic material that's present on the surface and whether the disinfectant can effectively penetrate that, or whether the presence of any residue might inactivate the disinfectant. And that's quite important when switching between 2 different disinfectants on rotation, because the residues of one disinfectant can well inactivate the other. And of course, there's the type and number of microorganisms present. Now, I mentioned earlier about resistance, and on the slide is a fairly kind of crude representation, hierarchy of resistance that a researcher into disinfectant activity called McDonald drew up in the late 1980s. So we have the population, the number of microorganisms. So it's often that a disinfectant logically will be more effective against a low number of microorganisms than a higher number. And then we have some microorganisms that are going to be more resistant than others. So for example, gram-negative bacteria are generally harder to kill than gram-positive non-sporing bacteria. And that's due to the extra material of the gram-negative organism's outer membrane. It's actually the lipopolysaccharide which causes endotoxin that actually confers a degree of resistance. And then we have generally fungal spores, and then we have the mycobacteria. So this is the organisms like tuberculosis, and they have a kind of a waxy cell coat that helps to prevent disinfecting activity. And then very near the top are bacterial spores, and of course there's prions as well, but that's only going to be a concern to certain types of biologic organisms, biological products, right? And then we have the location of microorganisms. So again, this comes back to how well the organisms are fixed to surfaces, and the greater the level of fixation, the harder they are to kill, which is another reason why biofilms are especially challenging. And we mentioned concentration earlier, but disinfectants are manufactured and then assessed against a particular concentration range, which is the proportion of chemicals to water. And then the contact time, which is the time required for the disinfectant to make contact with a given population and for the interactions between the chemical disinfectant and the cell wall to begin and for the disinfectant to penetrate and reach the particular target. So here the disinfectant must be left in contact with the surface, and with a non-sporicidal disinfectant, then this is typically 1 to 5 minutes depending upon the particular disinfectant. Temperature is another important factor, and there's an equation around something called quotient 10, but effectively it's that with every 10-degree rise in temperature, then the disinfectant activity tends to double, but conversely, with every 10 °C reduction in temperature, the disinfectant activity halves. And this is important because a lot of disinfectant efficacy testing and testing conducted by the manufacturer will be conducted at ambient temperatures. I think the disinfectant standards sets 20 degrees as the target. And then if you come to use that disinfectant in a cold room, for example, then chances are the contact time is going to be much longer, and that's something that you might need to evaluate. I've also touched upon different surfaces, and there are a number of studies that show variability on different surfaces. So for example, some studies suggest that, say you've got bacterial spores on enamel or aluminium, then these are harder to kill and require longer contact times compared with stainless steel. It also stands that surfaces need to be clean, which is a point I've made a couple of times, but in particular with sporicides, most sporicides are particularly weak when there is the presence of dirt on the surface. And there's also then the method of application. So we have in the old days what used to be called spray and pray. Well, that can be, we can get a greater degree of confidence if we actually wipe the surface. So the mechanical action, the pressure applied, can also help to, one, disassociate organisms from the surface, but also helps with the making the contact with the disinfectant to the organisms better as well. So wiping is really important. Now, just coming back to contact times, again, it's important that what we might do in the laboratory when we're assessing contact times is highly idealized. When we come into the clean room, then things might be a little bit different. We have to bear in mind also that it takes time to apply. And also, once the surface dries, then the activity either completely stops or at least reduces. So in our laboratory, we might have a low number of air change rates. That's going to be very different if we're applying the disinfectant underneath a unidirectional airflow with very rapid air changes in a very dry environment. So we might need to do a reapplication of the disinfectant so that the surface remains wet for the period of time that we want to assess that disinfectant over. We also need to consider on the basis of time stability. So if we are making disinfectants up in buckets, how long will that disinfectant remain active for? And also, even while we're using trigger sprays and so on, you know, what is the lifetime of that disinfectant? Is there any risk of ingress? And how are we assessing that shelf life? So they're also important concepts. So I've mentioned the act of testing, disinfectant efficacy testing. And unfortunately, with many areas of pharmaceuticals and healthcare, there is no agreed global standard. There are competing standards and competing approaches, particularly with with Europe, where there are the EN standards, and within the US, where they are the AOAC standards, and also some advice in the USP as well. However, although there are differences in how a test is conducted, the challenge organisms and acceptance criteria, disinfectant efficacy tests still fall into three main groupings. So there's basic suspension testing, a two-part simulated use test, which is a more robust test, and then the field trial, which is what happens when I actually take this disinfectant into my cleaning environment. And we'll quickly run through what those tests entail. So a suspension test used to be called a kill time method in the 70s, and it's a pretty crude test. Basically, here we are saying, does my disinfectant actually? So as the name suggests, it's having solutions of the disinfectant in test tubes and known populations of microorganisms, holding that for a contact time, stopping the activity with the use of a suitable neutralizer, and then measuring the surviving organisms. So it's a useful way of just saying, if you want to look between competing different disinfectants from new manufacturers, or if a new disinfectants come into market, but it's not really saying anything about what the disinfectant might do in real life. A step up from that is a quantitative suspension test, where there's an attempt to mimic real conditions a little bit more, and that's because the interfering substance is introduced into the test. Now, the standard calls for, or at least the European standard calls for, bovine albumin, which is a type of protein to be added. Here it's saying, well, okay, if we're not cleaning properly, does the disinfectant still work? So it allowed a slightly more accurate assessment of the disinfectant, but it's still not really giving us all the information that we need. There's far more importance around the surface test, which is sometimes called a carrier test or a coupon test. And it's this testing that the revised Annex 1 is alluding to, because here we're testing the disinfectant and the microorganisms against different individual surfaces. And coupon derives from using circular samples of the surfaces. So this would be the case of drying organisms onto the surfaces, which is actually quite tricky, and then applying the disinfectant and then neutralizing the activity, and then using some method to enumerate the surviving populations, which could be by plate counting or form of membrane filtration. And this is where you're going to get variance in terms of the different surfaces and the way organisms are acting with the material itself. And then whether we choose to do that as a static activity or choose to simulate that with mechanical activity. And then there are European standards now that give the basis for evaluating mechanical activity, as we might just apply the disinfectant, or in the form as if we were using a pre-saturated wipe as well. Also of equal importance is the field trial, which some would say is the ultimate verification of how good a disinfectant is. Now, no regulatory guidance exists, but essentially this is bringing the disinfectant into the area, rotating it, doing lots of environmental monitoring before we do this, doing environmental monitoring after, and looking for variations in recovery. It also establishes how long it takes to clean and disinfect. It can inform us how often to rotate. It can highlight problems like sticky surfaces, or where there might be health and safety issues arising, the degree to which we need to rinse surfaces after use, and even to help to inform about the effectiveness effectiveness of the environmental monitoring program. It also helps to develop the contact time, which I keep coming back to because it is probably fundamentally the most important aspect. The other thing with contact times, and when you're selecting between different disinfectants, you notice that a lot of the standards, so if you take the European standard for sporicides, which is a document EN 13704, it talks about a 60-minute contact time for a sporicide. If you're running a busy pharmaceutical operation, then you don't really...
Tim, sorry to interrupt. We're getting quite a few people who are saying you're fading in and out. I don't know if there's anything at your end that you can adjust.
Okay, let me try it again. Sorry about that.
That's all right.
Okay, so with the contact time, a number of parts of the standard talk about evaluating disinfectants over quite prolonged contact times. And 60 minutes appears in the standard EN 13704. The point I was saying was that if you're running a busy pharmaceutical facility, then using that kind of contact time is not very practical. So, I mean, it's very difficult to target it, but my personal view would be if you want to use a non-sporicidal disinfectant, really you want to be going for one with 5 minutes contact time. And then if you're using a sporicide, then be looking to target 10 to 15 minutes contact time. So that's just an important aspect to consider in relation to contact times. And then also really to, when you're carrying out also with disinfectant validation, is to weigh up just how dirty the conditions are that you might want to simulate, because ideally your conditions should be clean conditions. So there's probably a greater emphasis for carrying out qualifications with only a very slight level of soiling. Another aspect to consider with the validation exercise is with selecting the right microorganisms, because a lot of the standards are written for multi-industry. So some of the organisms quoted in the standard will be for, say, the food industry, for example, or the agricultural sector. So you really want to make sure that the organisms that are being used are reflective of the types of organisms that might appear in the particular facility. So generally you'll want to include a gram-positive coccus like a staphylococcus or micrococcus that would be representative of what might be shed from human skin. You want a gram-negative rod that will reflect water, so maybe a Pseudomonas type organism. A useful gram-positive non-sporing rod would be a Crinibacterium, because that can come from the human torso. Then you want to make sure you've got a yeast-like fungus like Candida, because that would be associated again with human skin. And then also a filamentous fungus as well. And then for sporicides, you need to be using a gram-positive sporing rod, typically a member of Bacillus species. And with fungi, you need to make sure that the fungus is in the spore state. Not often Aspergillus is used, and there are commercial populations of Aspergillus spores that can be purchased as well. It's often also expected these days that some of those isolates selected are isolates from your actual facility as well. Another area to consider is the target log reductions as well, because again, the standards sometimes have very, very high log reductions, yet within pharmaceutical clean rooms, we're dealing with relatively low levels of contamination. You can see on the slide there, for surfaces as measured with the contact plate, what the different maximal levels are within the different range of clean rooms. So targeting say a 3-log reduction for vegetative microorganisms and a 2-log reduction for spores should be adequate for clean room use. However, something important to bear in mind is that you should still target a relatively high inoculum. And that's because there's greater accuracy. Say if we had 10 to the power of 7 cells on a surface and we show that they reduce to 10 to the power of 4, that's a more accurate way of assessing the microbial cell count than starting with, say, 10 to the 4 and ending up with 10 to the 1. So that's another factor to consider within the validation program. It's also important that we consider the validation, the techniques within the validation as well. Although this doesn't negate the need for a field trial, this issue of how we actually mop, how we actually wipe a surface, and I've mentioned before the physical removal aspect and increasing the contact time aspect are really important, and we need to make sure we kind of capture that in some of the laboratory methods, and more importantly, that we're capturing that within the field trial. Now, just a few other quick aspects that need to be considered when we're using disinfectants. One is the issue of control. So it's important that we assess the certification of incoming disinfectants and subject them to a degree of lot control. So things like, is it the right material? Do the labels match the certificate? What's the expiry date? Is this supposed to be a sterile disinfectant? And make sure we practice good stock rotation. And this requires a quality control system to be in place. And this extends to having a defined method of preparation. So, and having procedures in place for recording the method of preparation and where we've used a particular disinfectant. And that operators are aware of how to prepare and how to use a disinfectant. So the underlying training is very important. And we want to have a good oversight by the microbiology laboratory. So we're tying in any fluctuations in environmental monitoring with our application of the cleaning and disinfection products, and that we're controlling things like shelf life and so on. And also there's going to be environmental considerations for the safe disposal of the disinfectant. Now, with the techniques, the way that we use cleaning and disinfection products is important, because although we may have gone to the trouble of validating them and we are controlling them, if they're not being used properly, then we are negating their effectivity. So it's very important to clean first and then apply the disinfectant, never the other way round. It's important that we're generally making up detergents in hot water, but disinfectants in cold, good quality pharmaceutical water, that we're cleaning from and disinfecting from the back of the room working out, and we're going from high down to lower surfaces. And it's also important within aseptic areas that both the detergent and the disinfectant need to be sterile. It's good practice that the materials we're using in aseptic areas are for single application, and also that they're non-particle shedding, because we don't want to be creating fibers that could potentially end up within the product, and that we're cleaning from the right parts of the room, and we're doing good techniques, things like double and triple bucket techniques, and doing things like the lift and pull technique now, which is again shown on the diagram on the slide. And the reason this is important is that if you get to the end of a surface, let's say you're wiping along a table, if you simply just stop, then all you're doing is pushing contamination to the end of the ledge. Where if you do the pull technique, then you're pulling up some of the contamination. It's also important to apply cleaning and disinfection products in straight lines, but to have slightly overlapping paths so that we don't miss anything. A question that commonly comes up is about the frequency of rotation, and there are no hard and fast rules to this. It's going to be partly what the field trial reveals. It's going to be partly on the grade of clean room, and it's going to be partly based on when the microorganisms recovered from environmental monitoring are reviewed, whether spore-forming organisms in particular are in control. But we also need to balance that with some of the aggressive nature of some sporicides. They're not great for stainless steel, particularly chlorine, and require extra wipes, and also with some of the health and safety measures that need to be in place. So kind of the last point I'd like to make is about the importance of ongoing monitoring. So we go to all this trouble of selecting disinfectants, qualifying disinfectants, improving the methods and so on. But our ultimate proof of how well cleaning and disinfection products are working is down to the assessment of the environmental monitoring program and having controls in place for controlling incoming materials and so on. But it's really about understanding variations in our microbiological data and the types of species that we're covering. And it's also good practice to periodically look for the most common microorganisms that we find and to go back and carry out aspects of the validation test to prove that what we're regularly finding within our facility can be killed against the disinfectants. And if we're proving they can be killed, then we're more likely to be veering towards poor techniques or inappropriate rotation. But if we do find something that has a degree of resistance, then we're more down the path of needing to change our disinfectant. So just in summary, what we've covered in this presentation are processes for selecting between different disinfectants and detergents, some of the global guidelines from the regulators together with common findings from inspection deficiencies, how to use disinfectants effectively, so that's all the things about time, temperature, contact times, some of the different approaches to validation and how the different standards differ, but also pharmaceuticals needs to wrestle out some of those nuances and develop appropriate criteria in terms of what we want to see in terms of log reductions and so on. And just concluding with the fact that the ultimate proof is within our environmental monitoring program. So they're the key points I want to get across. Sorry if there was a bit of fluctuation in sound, but hopefully the key messages have come across, and I'll pass you back over for your questions.
Okay, thank you, Tim. So that was got a quite nice little introduction to the disinfectant. I know it's quite a big area, and you have probably only scratched the surface of it, but I think that you've covered a lot of what people were asking during the webinar. But I do have some questions for you. I've got a question from a lady called Jane, and she said, does the rotation of the disinfectants with 2 include the sporicide, or is it 2 disinfectants and a sporicide?
Yeah, that's an interesting question, and it's also one that has caused a bit of confusion with the revision to EU GMP Annex 1, and it's one of, I know it's one of some of the professional bodies have written back in and asked for clarification. I think my own view is that you can look at this either way, and I think it depends upon what you're finding, the number of spores and the overall contamination in your program. So you can rotate between the 2, sporicide and non-sporicide, or you can select 2 different non-sporicides and periodically go in the sporicide at regular intervals. Obviously the second is probably preferable in terms of the health and safety issues and the aggressive nature of sporicides, but there's nothing wrong with the first one if that gives you your level of contamination control that you are seeking to achieve.
Okay, thank you. So I have another question from Eleanor, who said disinfectants have been tested against fungi and bacteria, but within the pharmaceutical industry, we're seeing a lot more of these new gene therapy biopharmaceuticals coming through using viral vectors. And with very little virucidal disinfectants available, how do you monitor for viruses, or do you monitor for viruses?
It's very, very difficult. There are disinfectant standards showing that you can put viruses onto surfaces, and if you have a disinfectant that claims to have virucidal properties, that you can eliminate it. But in terms of ongoing monitoring, then that's incredibly difficult and time consuming to do. My experience is that what most people do is focus on the viral security of their products and the viral inactivation steps that they have in place to get rid of any viruses in the product, and then will perform marker testing for the presence of any viruses of concern. So I think you can introduce that at the initial steps, but then I guess another complication is that there aren't that many laboratories attached to manufacturers that have the capability to handle viruses, so it might be something you need to hand out to a specialist laboratory. But for this, a lot of it you will be led by the names of the manufacturer and the type of viruses you're keen to eliminate. The good news in terms of the coronavirus is that most disinfectants are pretty effective at killing the coronavirus, and that's because it's a enveloped virus, which is easier to kill. So alcohol and hydrogen peroxide have both been called out as effective treatments.
Okay, I remember that from your previous webinar. Kelly asked, can you justify to not perform the suspension test at all in preference to just use surface testing and field trials when validating disinfectant efficacy?
Yes, I think you can. And I think there's been a great shift in the industry towards this. So I think with the suspension test, the manufacturer should have done most of this. The only reasons I think you might want to do that is if you've got particular environmental isolates that don't really feature in the manufacturer's data, and you're a little bit worried about how it's going to perform, the suspension test is a quick test, so you can check it against your environmental isolates before you launch into surface studies. But if you have a degree of confidence, then you can go straight into surface studies and accept the manufacturer's test data. Another area where the suspension test can be useful is if you're going to a new disinfectant and you've got 5 or 6 potentials to use and different companies are lobbying about buying their disinfectants, you could use that as a screening test to narrow down to the one that you want to take forward to surface studies, because surface studies are far more time consuming and expensive to run. So you don't want to take too many disinfectants forward to the surface study.
Okay, so I have a question from Bryony asking, how can cleaning be confirmed?
So there are some developments underway to try and assess the presence of residues on surfaces, so that conductivity probes that can be used. My experience is not that many people are using those. For cleaning validation, yes, there is. So if we're trying to clean a vessel or something, for the actual clean room, it still remains that it is an assessment of visual cleanliness, but it's also partly understanding the products as well. So There's less concern with residues with neutral detergents. And there are some disinfectants on the market that come as low residue to almost zero residue disinfectants. So we have greater confidence with those. On the other side, there's the complete belt and braces approach, which is to assume that there's always going to be residues. So you would need to do, or the company in that situation would always introduce, say, a WFI rinse or a alcohol rinse in between each detergent and disinfectant step. So again, there's no hard or fast rule, but it's something that you need to reach a position on, because it's a question that regulators are starting to ask more often, and also appears in the revision to Annex 1 as a concern.
And just one more question from Chris, and that is, how important is profiling microorganisms in relation to cleaning and disinfecting?
I think it's really important, and it's one of the things when I talk about environmental monitoring, in that it's not just about the numbers, it's about the types of microorganisms, and then knowing how effective your disinfectant is theoretically and then through efficacy studies against those microorganisms. Because if you do start particularly seeing bacterial and fungal spores, then that will trigger calls for concern. It may or may not be the disinfectant. It might be you've got a problem with the HEPA filter, or you've got a problem with transporting materials, or you've got a problem with the way or the frequency that people are actually applying the disinfectants. But you equally could have a concern. So you should keep, how often you might do one of these reviews is debatable. It might be 6 monthly or annual, but it's regularly coming up with what are the most common isolates. If they're overwhelmingly gram-positive cocci, then virtually every disinfectant should be able to treat those. If you start to see other organisms, then it's at least signalling that you need to take some kind of action, which might be the disinfectant.
That's good to know, especially as we've just invested in a new mouldy top here at RSSL. So hopefully we can put it to good use, helping identify those microorganisms. Thank you for attending our webinar. I hope you found it useful, and we appreciate all the questions you've asked. As I mentioned earlier, those questions we haven't been able to answer today, we'll get back to you along with the slides and the detailed white paper that Tim has written to supplement this webinar. Just a reminder that the final webinar in this 3-part autumn series will be taking place on Thursday, the 3rd of December, and will focus on sterility testing and overcoming difficult products. On behalf of the RSSL Sterile Manufacturing team, I would like to thank you for listening today, and please do not hesitate to contact me if you have any questions or you need our support for any projects. Thank you for your time.